My topic is about the quantum particle in a potential energy well. By now, we should all be familiar with the classic problem of a ball rolling in a potential energy well. And the way we go about solving this problem is that we would use conservation of energy, where we write the kinetic energy plus the potential energy equals the total energy of the ball. And we say that this total energy is constant throughout space, every point in space within that potential energy well. We can write the kinetic energy as 1/2 mv squared. And I can do this rather obscure thing where I multiply top and bottom with m. With that, we can rearrange the terms. And we notice that we have now mv, momentum. Now, this is actually a rather common way of writing kinetic energy, especially in quantum mechanics, as p squared over 2m. What we should realize is that our ball is a macroscopic object. And we've been dealing with physics at the macroscopic level, where we treat macroscopic objects as point particles at their center of mass. What we've been implicitly doing is that we've been using classical mechanics. And in classical mechanics, if we know the position of the particle and its momentum, then we can find its energy, its orbital period, or really everything else that we're interested in physics. However, if we go down and zoom in to the microscopic level, we realize that particles start to behave as waves more than point particles. And with waves, the position of a wave is no longer clear, nor its momentum. So to deal with these new waves, quantum mechanics was developed. In quantum mechanics, the way we describe our waves is that we describe it with a wave function denoted psi of x. With our wave functions, like the position and the momentum of the particle, we can find everything that we're interested in physics. A common interpretation of the wave function is that its square represents the probability of finding the particle at a certain location when we make a measurement. These peaks exhibit high probabilities of finding the particle whenever a measurement is made. And this relatively flat area represents a low probability of finding the particle when a measurement is made. Going back to our potential energy well, another thing that we realize in quantum mechanics is that the momentum is now represented by a derivative with respect to position, ddx. Now, notice that momentum is now an operator that acts on a function. It's no longer just a single value. To remind us of this operator, of P being an operator, we put hats on our P's. Plugging that into our equation, we get the second derivative because of the square. And we would act on our wave function, psi of x. In other words, multiply our wave function on the side. Now, it's pretty clear that our equation got a lot more complicated. And a particular obstacle of solving this equation is that there's no one-size-fits-all solution for all different potential energy well shapes. So for all the various shapes, we'll have to solve this equation on a case-by-case basis. A commonly solved potential energy well shape is a quadratic shape And the reason for that is within the minimum of any arbitrary potential energy well, this quadratic well shape is a pretty good approximation. The solutions even have their own name, called the quantum harmonic oscillator solutions. And that's an analogy to the classical harmonic oscillator of a spring mass system, whose potential energy is 1/2 kx squared. Now, if we go ahead and solve our equation, we get probability functions that look like this. Notice the center peak, the characteristic center peak, where the probability of finding the particle is the highest. A stark difference in quantum mechanics compared to classical mechanics is that we only have specific probability functions that we can fit into our potential energy well. And these specific functions happen at specific energy levels. This discretization of the energy values was coined quantization, and hence the name quantum mechanics. Notice that at the second energy level, we have 2 peaks. At the third, we have 3 peaks. At the fourth, we have 4 peaks. Now, this n values are just a convention. We just like to start with n equals 0. If we go up to really high energy levels, namely the 60th, we have around about 60 peaks. The solid line is the probability of finding a particle that we would get from quantum mechanics. And notice behind it, there's a subtle dashed curve. That's the probability that we would get from classical mechanics. Notice their similarities. They're both high probabilities on the edges. One way to interpret this is to go back to our classical macroscopic ball rolling in our potential energy well. And we notice that as the ball approaches the edges, it goes up the hill and it slows down. Therefore, it spends more time there and hence more likely to be found there. So the higher probabilities on the edges, which can be seen by our solutions, both from quantum mechanics and classical mechanics. Now, the takeaway from this slide is that from quantum mechanics, when we're solving problems in quantum mechanics, as we approach higher and higher energy levels, the quantum properties of our particles starts to fade away, and we approach the classical limit. This feature is often used when solving quantum mechanics problems to check our solutions, whether or not as we increase our energy and our size to the macroscopic level, whether or not we reduce our solution to the classical solution. And with that, I look forward to your questions.